My name is Lottie DeWitt, and today's lecture focuses on the topic of Laplace transforms. Today, we will be going through an introduction to the Laplace transform, including the definition of the transform, the linearity of the transform, and also combining transforms. We will then go through some usual Laplace transforms and properties of the transform. This section will include things like the transform of the derivative, the transform of higher order derivatives, the transforms of an antiderivative, and the derivatives of the transform. And then finally, we'll talk about the initial and final value theorems. After that, we will then go through the inverse Laplace transform, solving initial value problems, the Laplace transform and convolution, and finally, evaluating improper integrals using the Laplace transform. So first, we'll be doing our introduction to the Laplace transform. And during this section, we'll include the definition of the transform, the linearity of the transform, and also how we can combine multiple transforms. Laplace transforms belong to a very general class of objects called integral transforms. They are operators that take a function f, typically defined over the real numbers, and return a new function f hat, which is typically defined over the complex numbers. You have previously seen other examples of integral transforms. The most common is the Fourier transform, which was the topic of the previous lecture. In all generality, integral transforms are used to transform equations or problems that are difficult to solve in their original form into problems that can be addressed with easier mathematical tools. For example, Fourier transforms can be used to deal with a type of differential equation called boundary value problems. For example, solving something like u double prime of x plus u of x equals f of x for all x in x naught, x1, with u of x naught equals a and u of x1 equals b. In this lecture, we will focus on the Laplace transform. Its definition is as follows. Let f of t be a real valued function defined for all t greater than or equal to 0, with t being a real number. The Laplace transform of f is the function f of s is equal to the Laplace transform of f of s, which is equal to the integral of f of t times e to the negative ts dt from 0 to infinity. Here, s is equal to sigma plus I omega, which is a complex number, and sigma and omega are real numbers. The inverse Laplace transform is also formally given by f of t equals the inverse Laplace transform of f of s, which equals 1 over 2 pi I times the integral of f of s times e to the st ds from c minus I infinity to c plus I infinity, where c is chosen such that f of s has no singularity on the line from c minus I infinity to c plus I infinity in the complex plane. There are some notes that we need to consider when looking at the definition of the Laplace transform. First, f of s is a complex function defined over the complex numbers. Second, f of s is defined for all s where the previous integral converges. Third, making sense of the expression for the inverse transform requires some understanding of complex analysis, but we will not discuss this here. Instead, we will only consider practical ways in which you can calculate the inverse transform. Fourth, the convention is to denote the new function by a capital letter. So the Laplace transform of f equals capital F. And to use s as its variable, we say that the Laplace transform of f equals f of s. And lastly, s is, to some extent, a frequency. For practical applications, t is a time in seconds. And then s, for example, in f of s, will be expressed in 1/, seconds. Next, we want to build intuition for using Laplace transforms. The Fourier transform of a function f is only defined for functions that are integrable over the real numbers. In particular, it requires that the integral of the absolute value of f of t dt from negative infinity to infinity is less than infinity. This means that functions like f of t equals a, or f of t equals t to the n, and f of t equals e to the t do not have a well-defined Fourier transform. It is possible to make sense of the Fourier transform of these, but it requires extending the notion of a function to distributions. So we need to ask how we can alter the Fourier transform to deal with this type of function. One solution is artificially dampening the function f of t by something that's strongly decreasing. For example, we can choose e to the negative sigma t, where sigma is a real number. But this trick only works if the absolute value of f of t is bounded by ke to the alpha t for some k and alpha less than sigma. We will mostly be interested in functions defined for t greater than or equal to 0, which corresponds to this idea of positive time. We are interested in the evolution of the function f of t after an initial time t equals 0. We can now define the function f tilde of t equals f of t times e to the negative sigma t for t greater than or equal to 0 and 0 otherwise. Its Fourier transform is given by the Fourier transform of f tilde of omega sigma equals the integral of e to the negative I omega t times e to the negative sigma t times f of t dt from negative infinity to infinity, where sigma is a real number. We can then see that this equals the integral of e to the negative I omega t times e to the negative sigma t times f of t dt from 0 to infinity, since f of tilde of t is less than 0, which equals 0. And using basic algebra, we can see that this then equals the integral of e to the negative sigma plus I omega all times t times f of t dt from 0 to infinity. We know that s is equal to sigma plus I omega from earlier, and so we can rewrite this as the integral of e to the negative st times f of t dt from 0 to infinity, which then equals the Laplace transform of f of s. The natural intuition for the Laplace transform is that it corresponds to the Fourier transform of a dampened version of the function which is restricted to positive time. In particular, S is indeed a frequency, and we can expect some properties of the Fourier transform to still apply, like the existence of an inverse. Additionally, the real part of S corresponds to the damping, and so we usually require that the real part of S is greater than 0, which will ensure that the functions don't blow up. Let's now consider some examples of the Laplace transform. First, we have f of t equals 1 for t greater than 0. So let us begin by considering the Laplace transform of a constant function for t greater than 0. It is clearly bounded by an exponential. So f of t times e to the negative sigma t will be bounded for all sigma greater than 0. So then the Laplace transform of our function f of t equals 1 is equal to the integral of e to the negative st dt from 0 to infinity, which we can then see that is equal to negative 1 over s e to the negative st from 0 to infinity. Evaluating the bounds, we can see that this equals negative 1 over s times the limit as t goes to infinity of e to the negative st minus 1, which just equals 1 over s. We can apply the same approach to exponential functions. So let's consider the function f of t equals e to the at, assuming that the real part of s is greater than a with some constant a. Inputting our function, we can see that the Laplace transform of e to the at equals the integral of e to the at e to the negative st dt from 0 to infinity, which through basic algebra leads to e to the negative s minus a all times t dt from 0 to infinity. Then doing the integration gives us negative 1 over s minus a times e to the negative s minus a all times t dt from 0 to infinity. Applying the bounds then gives negative 1 over s minus a times the limit as t goes to infinity of e to the negative s minus a all times t minus 1, which then equals 1 over s minus a. We can even generalize this for complex exponential functions. So let's consider the function f of t equals e to the a plus bi times t for t greater than 0. Following the same procedure, we can input our function such that the Laplace transform of f equals the integral of e to the a plus bi times t times e to the negative st dt from 0 to infinity, which again, through basic algebra, leads to e to the negative s minus a minus bi all times t dt from 0 to infinity. Evaluating the integral, we can see that this becomes negative 1 over s minus a minus bi times e to the negative s minus a minus bi all times t from 0 to infinity. Then applying the boundaries gives us negative 1 over s minus a minus bi times the limit from t to infinity of e to the negative st minus 1. And we can see that this equals 1 over s minus a minus bi for the real part of s being greater than a, where this is the restriction to ensure that the transform actually exists. This formally requires integrating a complex function, but in this case, things go smoothly enough to just skip over the details. While we will discuss the global properties of the Laplace transform in a bit, the linearity of the Laplace transform is very useful for calculating the usual transforms. The theorem for the linearity of the Laplace transform is as follows. Let f of t and g of t be two functions with Laplace transforms f of s and g of s defined at least over the same domain, and a and b two numbers which could be either real or complex. Then the Laplace transform of A of AF plus BG of S equals A f of S plus B g of S. This directly follows from the Laplace transform's definition and the integral's linearity. We can then consider an example of the linearity of the transform. We can use the linearity of the transform to calculate the Laplace transform of the sine of t for t greater than or equal to 0. We can decompose the sine of t as a sum of two exponential functions, such that the sine of at equals 1 over 2I times e to the iat minus e to the negative iat. The Laplace transform of sine over the positive domain can then be calculated. We start by filling in the function such that the Laplace transform of the sine equals the integral of the sine of at times e to the negative st dt from 0 to infinity. Decomposing the sine of t as a sum of the two exponential functions then gives this as equaling the integral of 1 over 2I times e to the iat minus e to the negative iat times e to the negative st dt. We can then use the properties of integrals, which we learned in a previous lecture, to rewrite this as 1 over 2I times the integral of e to the iat e to the negative st dt from 0 to infinity minus the integral of e to the negative iat e to the negative st dt from 0 to infinity. We can now see that what we have is a sum of two Laplace transforms. This is something that's important to realize, and from here we can now proceed with the calculation again. We can rewrite the integrals in the Laplace transform notation, and then we get 1 over 2I times the Laplace transform of e to the iat minus the Laplace transform of e to the negative iat. We know from previous examples that the Laplace transform of e to the at equals 1 over s minus a. We can then see that the Laplace transform of e to the iat and the Laplace transform of e to the negative iat will equal 1 over s minus ai and 1 over s plus ai, respectively. If this isn't apparent to you, feel free to go through this example again for these specific Laplace transforms as an exercise. Therefore, our result becomes 1 over 2i times 1 over s minus ai minus 1 over s plus ai. We can then use basic algebra to rewrite the fractions over a common denominator such that we get 1 over 2i times s plus ai minus s minus ai all over s squared plus a squared. And then going through the final algebraic steps, we can see that this equals 1 over 2i times 2ai over s squared plus a squared, which equals a over s squared plus a squared. Beyond linearity, there are some essential properties of the Laplace transform that we need to go over before listing the transforms of the usual functions. We will now go through some of these. They do require long calculations, which I will do my best to go through slowly, but don't hesitate to pause the video if you need more time between steps. The first property is time dilation. which states that for a function f of t with Laplace transform f of s, and for a greater than 0, then the Laplace transform of f of a t equals 1 over a, f of s over a. To see where this property comes from, we can follow the same procedure that we've done before. First, we can write the Laplace transform in its integral format such that the Laplace transform of f of a t equals the integral of f of a t times e to the negative st dt from 0 to infinity. This then equals the integral of f of t prime times e to the negative st prime over a dt prime over a from 0 to infinity. Taking out the constant, we get 1 over a times the integral of f of t prime times e to the negative s over a times t prime dt prime from 0 to infinity. And solving this integral leads us to 1 over a times f of s over a. Another property is time shifting. And this states that for a function f of t with Laplace transform f of s, and for a constant a greater than 0, then the Laplace transform of f of t minus a equals e to the negative a s f of s. Again, we can see that this comes from substitution when we assume that everything is well defined. First, we can write the Laplace transform in its integral format such that the Laplace transform of f of t minus a equals the integral of f of t minus a times e to the negative st dt from 0 to infinity. We can then see that this equals the integral of f of t prime times e to the negative s times t prime plus a dt prime from a to infinity. Here, the boundary changes to a instead of 0 because of substitution. Splitting the exponential term, we can see that this equals the integral of f of t prime times e to the negative st prime times e to the negative as dt prime from a to infinity. Removing the constant term, we can see that e to the negative sa times the integral of f of t prime times e to the negative st prime dt prime from a to infinity. We can then extend the function so that it's 0 between t equals 0 and t equals a, such that the integral between 0 and a stays 0. This then means that it equals e to the negative sa times the integral of f of t prime times e to the negative st prime dt prime from 0 to infinity, which then equals e to the negative as f of s. Another property is that of frequency shifting, which states that for a function f of t with Laplace transform f of s, and for a constant a greater than 0, then the Laplace transform of e to the at f of t equals f of s minus a. We can see that this is the exact opposite process as before. The Laplace transform of e to the at f of t equals the integral of e to the at f of t times e to the negative st dt from 0 to infinity. This then equals the integral of f of t times e to the negative s minus a times t dt from 0 to infinity. This then gives us the final result of f of s minus a. The next property is convolution, which states that for two functions f of t and g of t with Laplace transforms f of s and g of s, where we denote the convolution of f and g as f star of g, then the Laplace transform for the convolution of f and g of t equals f of s, g of s. This calculation is a bit longer, and we need to extend f of t and g of t so that they are 0 for t less than 0. For the first few steps, we will be inverting the order of operations one step at a time. To make that clearer as we go through it, I've colored the steps in question. So the Laplace transform for the convolution of f and g of t equals the double integral of f of tau g of t minus tau d tau times e to the negative st dt, with the first integral from 0 to infinity and the second from negative infinity to infinity. We then invert the order of our operations such that the d tau and dt are next to each other, and this is shown in blue. This leads to the double integral of f of tau g of t minus tau times e to the negative st d tau dt, with the first integral from 0 to infinity and the second from negative infinity to infinity. On the second line, we begin by inverting the order of operations of the integrals such that we get the double integral of f of tau g of t minus tau times e to the negative st d tau dt, with the first integral from negative infinity to infinity and the second from 0 to infinity. We then separate the f of tau from the second integral as seen in orange. To get the integral of f of tau from negative infinity to infinity times the integral of g of t minus tau times e to the negative st d tau dt from 0 to infinity. Moving from the second to the third line, we're going to replace the second integral, or the integral of g of t minus tau times e to the negative st d tau dt from 0 to infinity, with the Laplace transform of g of t minus tau. Thus, in the third row, we get the integral of f of tau times the Laplace transform of g of t minus tau d tau from negative infinity to infinity. This then leads us to the integral of f of tau times e to the negative s tau g of s d tau from negative infinity to infinity. On the fourth line, we remove the g of s from the integral as its constant, such that we get g of s times the integral of f of tau times e to the negative s tau d tau from negative infinity to infinity. Extending f of t and g of t so that they are 0 for t less than 0 gives g of s times the integral of f of tau times e to the negative s tau d tau from 0 to infinity, which just equals f of s, g of s. This then leads to our last property, called conjugation, which states that for a complex function f of t, the transform of its complex conjugate f bar is given by the Laplace transform of f bar of t equals f of s bar bar. We can see that this comes from the definition. First, the Laplace transform can be equated to its integral format such that the Laplace transform of f bar of t equals the integral of f bar of t times e to the negative st dt from 0 to infinity. We can then see that this equals the integral of f of t times e to the negative st bar dt all bar, since z double bar equals z and the conjugation is linear. This then equals the integral of f of t times e to the negative s bar t dt all bar, since e to the z all bar equals e to the z bar. This means that this equals f of s bar bar. Next, we will go through some usual Laplace transforms. We will look at the Dirac delta function, the shifted Dirac delta function, the Dirac comb, power functions, step functions, rectangular pulses, power exponential functions, and also some trigonometric functions. Now that we have established some important properties of the Laplace transform, we can start by listing common Laplace transforms. In addition to the properties above, it is useful to be familiar with integration techniques such as integration by parts or by substitution in order to be able to calculate Laplace transforms in the wild. Unless explicitly specified, we will assume that all the functions we will encounter are well defined from 0 to infinity. If needed, we will extend them to negative infinity by giving them a value of 0 for t less than 0. More formally, this corresponds to multiplying the function f of t defined on the real numbers by the Heaviside step function theta, which is defined such that theta of t greater than or equal to 0 equals 1, and theta of t less than 0 equals 0. First, we will look at the unit impulse, or the Dirac delta function. The Dirac delta function is one of the cases where it isn't really a function, but a distribution. It is, however, so widespread that it's useful to be familiar with it. It is defined by the Dirac function of t equals 0 if t is not equal to 0, and undefined if t equals 0. It does, however, have a well-defined integral. The integral of the Dirac function of t dt from negative infinity to infinity equals 1. While it technically doesn't match the conditions for having a Laplace transform, we can still define one if we understand the Dirac delta as a distribution. We can then calculate the Laplace transform such that the Laplace transform of the delta of t equals the integral of the delta of t times e to the negative st dt from 0 to infinity. This then equals the integral of the delta of t times e to the negative st dt from 0 from the left to 0 from the right, where we know that the delta equals 0 for t not equal to 0 by definition. This then equals e to the negative 0 times the integral of delta t dt from 0 from the left to 0 from the right, since e to the negative st is continuous at 0. This then equals 1 times the integral of the delta of t dt from negative infinity to infinity, since, again, delta is equal to 0 for t not equal to 0. We can finally see that this is just equal to 1. Therefore, the Laplace transform of the complicated delta function is a simple constant function of 1. The top graph here shows the graph of the Dirac delta function, while the bottom shows how the graph changes when you graph the Laplace transform for real values of s. We can then consider the shifted direct delta function. The delta function from before corresponds to an impulse at a time t equals 0. However, it often happens that we are interested in impulses at non-zero time, but after some delay tau, so the delta of t minus tau. We can use the time-shifting property of the Laplace transform that we discussed earlier. So then the Laplace transform of delta t minus tau equals e to the negative tau s times the Laplace transform of delta t, which equals e to the negative tau s. The top graph here shows the graph of the shifted direct delta function, where we can see the delayed impulse at tau. The bottom graph shows how this changes when we graph the Laplace transform for real values of s. We can then go one step further and consider what happens if we add infinitely many Dirac functions. This is called the Dirac comb. The Dirac comb is denoted by the triple I of t, which is shown here in blue. Since the Dirac comb is the addition of infinitely many Dirac functions, we can see that the comb is equal to the sum from k equals 0 to infinity of the delta of t minus kt. Intuitively, it is just a sum of impulses. So an example might be a heart monitor that would just never stop. Using the time-shifting property and linearity, we can see that the comb equals the sum from k equals 0 to infinity of the Laplace transform of the delta of t minus kt. This is then equal to the sum from k equals 0 to infinity of e to the negative skt, which can be rewritten as the sum from k equals 0 to infinity of e to the negative st all to the k power. And this then simplifies to 1 over 1 minus e to the negative st. The top graph in blue shows the graph of the Dirac comb function, where we can see the multiple impulses. And the bottom shows the graph of this Laplace transform for real values of s. We will now go back to functions that are more well-behaved, namely monomials of the form t to the n, with n in the natural numbers. We will also only consider s such that the real part of s is greater than 0. We have already seen that the Laplace transform of t to the 0 equals 1 over s. So we can move on to the next monomial, f of t equals t. The graph here shows what the function f of t equals t looks like in the positive domain. We can calculate the Laplace transform using the method of integration by parts, which we saw in the earlier integration lecture. The Laplace transform of t equals the integral of te to the negative st dt from 0 to infinity. Then, using integration by parts, we can see that this equals negative 1 over s e times negative st t from 0 to infinity plus the integral of 1 over s e to the negative st dt from 0 to infinity. Solving this and rewriting in terms of the Laplace transform, we can see that this equals 0 plus 1 over s times the Laplace transform of 1, which we know equals 1 over s squared. The bottom graph here now shows the graph of this Laplace transform for real values of s. Ultimately, we want to calculate any Laplace transform of t to the n for n in the natural numbers. But the next step is to calculate the Laplace transform of t squared. Again, we will use integration by parts. First, the Laplace transform of t squared can be written in its integral format such that it equals the integral of t squared times e to the negative st dt from 0 to infinity. Then, using integration by parts, we get negative 1 over s e to the negative st t squared from 0 to infinity plus the integral of 2t 1 over s e to the negative st dt from 0 to infinity. This then gives 0 plus 2 over s times the Laplace transform of t, which we know equals 2 over s cubed. The top graph shows the graph of the function t squared, and the bottom shows the graph of this Laplace transform for real values of s. We can then keep going and expand this again to t to the n for n in the natural numbers. We can see that the Laplace transform of t to the n equals the integral of t to the n e to the negative st dt from 0 to infinity. Using integration by parts and repeating the same steps as earlier, we can see that this equals negative 1 over s e to the negative st t to the n from 0 to infinity, plus the integral of n t to the n minus 1, 1 over s e to the negative st dt from 0 to infinity. This then equals 0 plus n over s times the Laplace transform of t to the n minus 1, which equals n times n minus 1 over s squared times the Laplace transform of t to the n minus 2. This will then equal n factorial over s to the n plus 1. Again, the top graph here shows the function t to the n for n in the natural numbers, and the bottom shows how this changes when we graph the Laplace transform for real values of s. It should be noted that we can apply the same reasoning to find the Laplace transform of t to the q, with q being a fraction, such that the Laplace transform of t to the q equals the gamma function of q plus 1 over s to the q plus 1. Feel free to try this at home, but it does require much more tedious algebra. We can also combine these with the shifting and scaling rules that we've seen before. One important example of this is the delayed step function, which we can see in the top graph. The delayed step function is defined by theta of t minus tau, which is 0 if t is less than tau and 1 if t is greater than or equal to tau. Here, tau is, in all generality, a delay. It corresponds to a system that's been activated after a delay. The corresponding Laplace transform of theta of t minus tau equals e to the negative s tau over s. The bottom graph shows how this changes when we graph the Laplace transform for real values of s. We can then combine multiple step functions to create a rectangular pulse. We define this function as f of t equals theta of t minus tau 1 minus theta of t minus tau 2, which corresponds to a system activated after a delay. The Laplace transform for the function is given by the Laplace transform of theta of t minus tau 1 minus the Laplace transform of theta of t minus tau 2. Solving this, we can see that we get e to the negative s tau 1 over s minus e to the negative s tau 2 over s, which can be rewritten over a common denominator to get e to the negative s tau 1 minus e to the negative s tau 2 over s. Again, the bottom shows the graph of the Laplace transform for real values of s. Using the frequency shifting rule, we can get the Laplace transform of a very important and very general class of functions known as the delayed power exponential functions, which are defined by the function f of t equals t minus tau all to the n times e to the negative alpha times t minus tau. Here again, sigma is some real number. Using the rules and procedures we've used earlier, we can then find the Laplace transform of this function. Inserting the function into the Laplace transform results in e to the negative s tau times the Laplace transform of t to the n e to the negative alpha t. This can be rewritten as e to the negative s tau times the Laplace transform of t to the n of s plus alpha. This can be solved to equal n factorial times e to the negative s tau all over s plus alpha to the n plus 1. Again, the top graph shows the function in question, while the bottom shows the graph of this Laplace transform for real values of s. One relatively simple but common case of functions involving exponents is the exponential approach. Like the function f of t equals 1 minus e to the negative alpha t, where alpha is some real constant. This corresponds, for example, to a system relaxing to its equilibrium state, like a capacitor charging in an RC circuit. We can see that the Laplace transform is given by the Laplace transform of 1 minus the Laplace transform of e to the negative alpha t. We have seen this before, and we can recognize them as 1 over s minus 1 over s plus alpha, which can just be rewritten as alpha over s times s plus alpha. Again, the top graph shows the function in question, while the bottom shows the graph of this Laplace transform for real values of s. We can now move to consider trigonometric functions. Earlier, we saw that the Laplace transform of the sine of at is equal to a over s squared plus a squared. The same reasoning can be applied to the cosine function shown in the blue top graph. The Laplace transform of the cosine of at equals 1/2 times the Laplace transform of e to the iat plus e to the negative iat. We have seen these earlier, and so we can write that this is equal to 1/2 times 1 over s minus ai plus 1 over s plus ai. And through algebraic manipulation, we can see that this becomes 1/2 times s minus ai plus s plus ai over s squared plus a squared, which then simplifies to s over s squared plus a squared. The bottom graph again shows the graph of this Laplace transform for real values of s. In real situations, oscillating systems cannot be described by a perfect cosine wave as the oscillations are damped. For example, consider friction slowing down a pendulum. We can describe this by an exponential term such that f1 of t equals e to the negative at sine of bt, and f2 of t equals e to the negative at cosine of bt. Using the frequency shift rule, we can see that the Laplace transform of f1 equals b over s plus a all squared plus b squared, and the Laplace transform of f2 equals s plus b all over s plus a all squared plus b squared. You can find these by following the same procedure that we've done on the previous slides. We can use the same approach that we used for the usual trigonometric functions to calculate the Laplace transforms of the hyperbolic trigonometric functions. The hyperbolic sine of at is defined as e to the at minus e to the negative at all divided by 2. And the hyperbolic cosine of at is defined by e to the at plus e to the negative at all divided by 2. Using the frequency shift rule and the linearity of the Laplace transform again, we can see that the Laplace transform of the hyperbolic sine of at equals 1/2 times 1 over s minus a minus 1 over s plus a, which just equals a over s squared minus a squared. And the Laplace transform of the hyperbolic cosine of at equals 1/2 times 1 over s minus a plus 1 over s plus a, which equals s over s squared minus a squared. This leads us to our next section, which is the properties of the Laplace transform. This section will include the transform of the derivative, the transform of higher order derivatives, the transforms of an antiderivative, the derivatives of the transform, and finally, the initial and final value theorems. As mentioned earlier, the Laplace transform is typically used to deal with differential equations. We first need to find out how we can calculate the Laplace transform of the derivative f prime of t of a function f of t. The property, called the transform of a derivative, states that for a function f of t with Laplace transform f of s, then the Laplace transform of f prime of t equals s f of s minus f naught. We can show this property using integration by parts. The Laplace transform of f prime of t equals the integral of f prime of t e to the negative st dt from 0 to infinity. Using integration by parts, we can see that this equals f of t e to the negative st from 0 to infinity minus the integral of f of t times negative s e to the negative st dt from 0 to infinity. This equals 0 minus f of 0 plus s times the integral of f of t e to the negative st dt from 0 to infinity, since f of t is bounded by some ke to the alpha t, where alpha is just some real constant. This then equals s f of s minus f naught. Therefore, we can see that the transform of a derivative involves the initial value of the function f of t. We can iterate this process to get the Laplace transform of higher order derivatives. For the second derivative, we can see that the Laplace transform of the second derivative of f of t equals s times the Laplace transform of f prime of t minus f prime of 0. Inputting the result of the first derivative shows that this equals s times s f of s minus f naught minus f prime of 0. This then equals s squared f of s minus s of f naught minus f prime of 0. Here, the transform of the second derivative involves the initial value of the function and its derivative. Using a very similar approach, we can show the following property for the transform of higher order derivatives. It states that for a function f of t with Laplace transform f of s, writing the ith derivative of fi of t, we have the Laplace transform of fn of t equals s to the n f of s minus s to the n minus 1 f naught minus dots minus s f prime naught minus f naught. In general, the Laplace transform of the nth derivative involves the initial value of the first n minus 1th derivatives. We can proceed similarly to find the Laplace transform of the antiderivative of a function. This will be useful when considering integral differential problems. For those not familiar with the wording, an integral differential equation is just an equation that involves both integrals and derivatives of a function. Then, the transform of an antiderivative is stated as: for a function f of t with Laplace transform f of s, then the Laplace transform of the integral of f of tau d tau from 0 to t equals f of s over s. This is again something we can show using integration by parts. We see that the Laplace transform of the integral of f of tau d tau from 0 to t equals the integral of e to the negative st dt from 0 to infinity times the integral of f of tau d tau dt from 0 to t. This then equals e to the negative st over negative s times the integral of f of tau d tau from 0 to infinity plus 1 over s times the integral of e to the negative st f of t dt from 0 to infinity. We can see that this becomes 0 minus 0 plus 1 over s times the integral of e to the negative st f of t dt from 0 to infinity, which just equals f of s over s. The first term is 0 because f of t is bounded by some ke to the alpha t. And the second term is also 0 because we are only integrating the function over a point. Knowing how to take the derivative of a Laplace transform can be useful. While we will not discuss in detail the conditions for the existence of such a derivative, we can show the following property. For a function f of t with Laplace transform f of s, then the derivative df of s over ds equals the Laplace transform of negative t f of t. So let's work through a proof of this. The Laplace transform of negative t f of t equals the integral of negative t f of t e to the negative st dt from 0 to infinity. which we can then rewrite as the integral of f of t times dE to the negative st over ds dt from 0 to infinity. Then this equals the integral of d over ds times f of t e to the negative st dt from 0 to infinity, since f of t is independent of s. This then equals d over ds times the integral of f of t e to the negative st dt from 0 to infinity, since t and s are independent. And solving the integral, we find that this in fact equals df of s over ds. We can apply this to higher order derivatives by similarly iterating the proof. For a function f of t with Laplace transform f of s, then we can see that d to the n f of s over ds to the n equals the Laplace transform of -1 to the n t to the n f of t. We can also show a very similar property for the integral of a Laplace transform. For a function f of t with Laplace transform f of s, then the integral of f of sigma d sigma from s to infinity equals the Laplace transform of f of t over t. This leads us to the initial value theorem. We can relate the Laplace transform of a function to its initial value. This will be important when using Laplace transforms to solve differential equations. The theorem states that for a function f of t with Laplace transform f of s, then when f of 0 plus is well defined, that the limit as t goes to 0 plus of f of t is equal to f of 0 plus, which is equal to the limit as s goes to infinity with s in the real numbers of s f of s. It is important to note that here we use the value of f of t at t equals 0 plus, which means right after the start. For example, for a step function, f of 0 minus equals 0, while f of 0 plus equals 1. There is a similar theorem called the final value theorem. This describes the final value or the behavior of the function f of t at infinity. This is related to the Laplace transform at s to 0. The final value theorem states that for a function f of t with Laplace transform f of s, that when the limit as t goes to infinity of f of t is well defined, then the limit as t goes to infinity of f of t equals the limit as s goes to 0 for s in the real numbers of s f of s. The same note applies here about 0 plus and 0 minus. This leads us to the inverse Laplace transform. We said earlier that the Laplace transform can be used to solve some differential equations. In order to do this, we will usually need to transform back the functions from the Laplace domain to the temporal domain. For this, we will have to find a way to calculate the inverse Laplace transform, which we defined earlier as f of t equals the inverse Laplace transform of f of s equals 1 over 2 pi I times the integral of f of s e to the st ds from c minus I infinity to c plus I infinity. We can also see that we can write the inverse Laplace transform as a linear operation, such that the inverse Laplace transform of A f of s plus B g of s equals A times the inverse Laplace transform of f of s plus B times the inverse Laplace transform of g of s. Unfortunately, this is usually difficult to calculate and requires the notion of complex analysis beyond the scope of this lecture. If you are interested, however, computing this integral can be done using Cauchy's residue theorem. Luckily, however, we now know a lot of different Laplace transforms for usual functions. And we can use this to our advantage and recognize the function f of t whose transform is f of s. Laplace transforms will usually take the form of a polynomial fraction. The goal will usually be to simplify the fraction by using partial fraction decomposition, which we also covered in the integration lecture, and then use the list of known Laplace transforms to go back to the temporal domain and get f of t. Even though we went through an example of partial fraction decomposition in the integration lecture, we will do another example here since it is such a commonly used technique. Let's consider the function f of s equals p of s over q of s, which equals 3s squared plus 8s plus 15 all over s times s plus 1 squared plus 4. We know that we want to find a solution which has the form f of s equals a over s plus b over s plus 1 squared plus 4. We start by expanding the numerator after cross-multiplying to get both fractions over the same denominator. So p of s equals a times s plus 1 squared plus 4 plus b times s. Expanding the first section gives us a times s squared plus 2s plus 5 plus bs. Then factoring out an s from the middle gives as squared plus 2a plus b times s plus 5a. Now, we know that we originally started with a numerator of 3s squared plus 8s plus 15. And so we can see that a must be equal to 3 and b must be equal to 2 since 6 plus b equals 8. Therefore, we can rewrite f of s as f of s equals 3 over s plus 2 over s plus 1 squared plus 4, which equals 3 over s plus 2 over s plus 1 squared plus 2 squared. If we write 4 as 2 squared, we will have a much easier time in the next slide. Using the last expression where we found that f of s was equal to 3 over s plus 2 over s plus 1 squared plus 4, which then equals 3 over s plus 2 over s plus 1 squared plus 2 squared, we can look in the list of known Laplace transforms for the two pieces. So firstly, for the Laplace transform of f of 1 of t, which equals 3 over s, and secondly, for the Laplace transform of f2, which equals 2 over s plus 1 squared plus 2 squared. We can recognize that f1 of t equals 3 and the Laplace transform of f of t equals 1 is 1 over s. Through linearity, we get that the Laplace transform of 3 equals 3 times the Laplace transform of 1 equals 3 over s. This is, though, of course, only valid for t greater than 0. For f2 of t, we recognize that we have something of the form the Laplace transform of f2 of t equals b over s plus a squared plus b squared, where a equals 1 and b equals 2. What we can notice is that we saw this form earlier on slide 23, and that this just corresponds to the damped sine function, which means that f2 of t equals e to the negative t sine of 2t. Now we can group all of our terms together to get the final result. So the inverse Laplace transform of 3s squared plus 8s plus 15 all over s times s plus 1 squared plus 4 equals 3 plus e to the negative t sine of 2t. This technique works well for Laplace transforms that look like rational fractions. If there are exponential terms in the numerator, then they can easily be removed by using the time shifting technique that we spoke about earlier. Now that we have looked at both the Laplace transform and the inverse Laplace transform, we can take a closer look at solving initial value problems. We have mentioned multiple times that Laplace transforms are very useful for solving initial value problems. This is because we have a practical way of computing the Laplace transform of the derivative of a function. We can illustrate this using a first-order constant coefficient linear differential equation. V dot of t plus gamma of vt equals f of t, with initial conditions v naught is equal to VO. This corresponds, for example, to the equation of motion of a point mass with some friction with a coefficient gamma. The function f of t is a forcing term. For example, if we are accelerating the point mass with constant acceleration between t equals 0 and t equals tau, then we could write that f of t equals theta of t minus theta of t minus tau. We will solve this by taking the Laplace transform of the differential equation. The Laplace transform of gamma v of t equals gamma v of s. The Laplace transform of v dot of t equals s vs minus v0. And the Laplace transform of f of t equals f of s, which equals 1 minus e to the negative s tau all over s. We can then take the Laplace transform of the whole equation. So s v of s minus v0 plus gamma v of s equals 1 over s minus e to the negative s tau over s. Then v of s times s plus gamma equals VO plus 1 over s minus e to the negative s tau over s. And finally, V of s equals V0 over s plus gamma plus 1 over s times s plus gamma minus e to the negative s tau over s times s plus gamma. From here, we can recognize three Laplace transforms from our list. For the first term in blue, we can see that V0 over S plus gamma equals VO times 1 over S plus gamma. This then equals VO times the Laplace transform of e to the negative gamma t, which is on our known list of Laplace transforms. For example, see slide 6. For the second term in orange, we can see that 1 over s times s plus gamma equals 1 over gamma times gamma over s times s plus gamma. This then equals 1 over gamma times the Laplace transform of 1 minus e to the negative gamma t. This is a Laplace transform of the exponential approach, which you can see on slide 21. For the third term in purple, we can see that e to the negative s tau over s times s plus gamma equals e to the negative s tau times 1 over gamma times gamma over s times s plus gamma. We can see that the last part of this is the same as we had in the second case, and so this equals e to the negative s tau times 1 over gamma times the Laplace transform of 1 minus e to the negative gamma t, which is the Laplace transform of the exponential approach. Again, see slide 21. And finally, we can rewrite this as 1 over gamma times the Laplace transform of 1 minus e to the negative gamma times t minus tau. This is just the time shifting property. Regrouping all three terms, we can see that v of s equals v0 times the Laplace transform of e to the negative gamma t plus 1 over gamma times the Laplace transform of 1 minus e to the negative gamma t minus 1 over gamma times the Laplace transform of 1 minus e to the negative gamma times t minus tau. We can then write all the parts within the Laplace transform notation, such that v of s equals the Laplace transform of VO e to the negative gamma t plus 1 over gamma e to the negative gamma t minus 1 over gamma times 1 minus e to the negative gamma times t minus tau. This can then be simplified to the Laplace transform of V0 e to the negative gamma t minus 1 over gamma times e to the negative gamma t minus e to the negative gamma t, or negative gamma times t minus tau. We can then see that the section inside the Laplace transform notation gives us v of t, such that v of t equals VO e to the negative gamma t minus e to the negative gamma t minus e to the negative gamma times t minus tau all over gamma. We can apply a very similar method to solve higher order differential equations. We can illustrate this with the second order differential equation, which gives the motion of the damped harmonic oscillator responding to a sudden acceleration. This would, for example, correspond to a point mass attached to a spring and suddenly being released at t equals 0. The equation of motion can then be written at t greater than or equal to 0 as d squared x over dt squared plus 2 gamma dx over dt plus omega naught squared x of t, which equals f of t, which equals g theta of t. Written this way, omega naught is the natural frequency of the system, gamma is a damping coefficient, and g is a constant acceleration turned on at t equals 0. We will also assume that initially the oscillator is at rest, so x of 0 equals 0 and dx over dt of 0 is also 0. Using the equation of motion from the previous slide, we can take the Laplace transform of each term. The Laplace transform of the first term, d squared x over dt squared, shown in blue, equals s squared ds minus s x of 0 minus x prime of 0, which equals s squared x of s. The Laplace transform of the second term, 2 gamma dx over dt, shown in orange, equals 2 gamma times s, x of s, minus x of 0, which equals 2 gamma s, x of s. The Laplace transform of the third term, omega naught squared, x of t, shown in purple, equals omega naught squared x of s, and the Laplace transform of the last term, g theta of t, shown in yellow, equals g times 1 over s. The Laplace transform of the equation is therefore s squared x of s plus 2 gamma s x of s plus omega naught squared x of s equals g over s. And we can rewrite this as x of s equals f naught times g over s times s squared plus 2 gamma s plus omega naught squared. We can see that the term in brackets in the denominator can be written as s squared plus 2 gamma s plus omega naught squared equals s plus gamma squared minus gamma squared plus omega naught squared. We can then rewrite this as s plus gamma squared plus omega naught squared times 1 minus gamma squared over omega naught squared. And this we will rewrite as s plus gamma squared plus double or omega r squared, where omega r is defined as omega naught times the square root of 1 minus gamma squared over omega naught squared. We can then rewrite x of s as x of s equals g times 1 over s times s plus gamma squared plus omega r squared. From there, the standard approach would be to decompose the right-hand side into partial fractions and to take the inverse Laplace transform of each term, which would give you x of t. However, here we can note that we can rewrite the equation as s x of s equals g times 1 over s plus gamma squared plus omega r squared. Here we can recognize that s x of s equals the Laplace transform of dx over dt, since dx over dt of t equals 0 equals 0. The Laplace transform then gives that dx over dt equals g times the inverse Laplace transform of 1 over s plus gamma squared plus omega r squared. Looking at the table of known integrals, we can then see that dx over dt equals g over omega r times the inverse Laplace transform of omega r over s plus gamma squared plus omega r squared, which equals g over omega r times e to the negative gamma t times the sine of omega r t. We can then solve for x of t by using integration by parts, which gives us x of t equals k minus e to the negative gamma t times gamma sine of omega r t plus omega r cosine of omega r t, all divided by omega r squared plus gamma squared. And this equals k minus e to the negative gamma t times gamma sine of omega r t plus omega r cosine of omega r t, all divided by omega naught squared. The constant k here is determined by x of 0 equals 0. And so k equals omega r over omega naught squared. This then leads us to the Laplace transformation and the property of convolution. One other important use of the Laplace transform comes from the fact that the transform of the convolution of two functions, f of t and g of t, is simply the product of their respective Laplace transforms, f of s, g of s. Consider the example of the convolution of f of t and g of t. Let us consider specifically the convolution of a step impulse from t equals 0 to t equals tau of f of t equals theta t minus theta t minus tau, with a decaying exponential g of t equals e to the negative at. We can then write the Laplace transform as the Laplace transform of the convolution of f of t and g of t equals the Laplace transform of f of t times the Laplace transform of g of t. From earlier examples, we can see that inputting our functions and taking the Laplace transform gives the result equal to 1 minus e to the negative tau s over s times a over s plus a. And this then equals a over s times s plus a minus e to the negative tau s times a over s times s plus a, which we can then write as the Laplace transform of 1 minus e to the negative at minus e to the negative tau s times the Laplace transform of 1 minus e to the negative at. And this then equals the Laplace transform of 1 minus e to the negative at, theta, minus the Laplace transform of 1 minus e to the negative a times t minus tau times theta of t minus tau. So then the convolution of f of t and g of t equals 1 minus e to the negative at times theta of t minus 1 minus e to the negative a times t minus tau times theta of t minus tau. The bottom graph here shows the graph of the Laplace transform for the convolution for real values of s. This leads to our final section on evaluating improper integrals using the Laplace transform. Finally, there are some cases where the Laplace transform can be used to evaluate improper integrals. One such significant example is the integral of the sine of x over x from negative infinity to infinity, and this is called the Dirichlet integral. This function has multiple important applications in physics and engineering since it is the Fourier transform of a rectangular window. However, none of the usual integration tricks will work here. The first step is to note that the function is even. So the integral of the sine of x over x dx from negative infinity to infinity equals 2 times the integral of the sine of x over x dx from 0 to infinity. We can now use the relation for the integral of a Laplace transform, where the Laplace transform of f of t equals f of s, such that the integral of f of sigma d sigma from 0 or from s to infinity equals the Laplace transform of f of t over t. And so the integral of f of sigma d sigma from 0 to infinity equals the limit from s to 0 of the Laplace transform of f of t over t. Taking f of t equals the sine of t, then we can write that the Laplace transform of the sine of t over t equals the integral of the Laplace transform of the sine of sigma d sigma from s to infinity. This then equals the integral of 1 over 1 plus sigma squared d sigma from s to infinity. And we can find that this equals the arctangent of sigma from s to infinity. And evaluating the bounds gives us pi over 2 minus the arctangent of s. Going back to the definition of the Laplace transform, we can also write that the Laplace transform of the sine of t over t equals the integral of the sine of t over t times e to the negative st dt from 0 to infinity. Equating the two terms and taking the limit when s goes to 0, then we see that the integral of the sine of t over t dt from 0 to infinity equals pi over 2, and that the integral of the sine of t over t dt from negative infinity to infinity equals pi. This then leads us to the conclusion of this lecture on Laplace transforms. Laplace transforms can feel overwhelming and like a lot of material to learn, but there are a few key transforms and properties that I've summarized in the conclusion. The first two conclusion tables will give you common Laplace transform pairs for things that we've covered in the lecture. And the final conclusion table will give you common Laplace transform properties that we've also covered. Feel free to take your time going through them and also to use them as reference when you go throughout your studies. Thank you.